Hello. In the last 3 lectures, we discussed compliant mechanisms, all the perspective overview, and then the spirit of compliant mechanisms as well as some applications. Now, let us get to the details. One of the first thing that one would want to learn about whenever we consider mechanisms is mobility analysis. In fact, a mechanism design is all about how we can constrain various bodies. In the case of rigid link mechanisms, all the rigid bodies connected with joints so that they move in a manner that we want them to move. In compliant mechanisms, it is not different. That is why we begin first with mobility analysis. So, if we look at the mobility analysis, the first concept that we need to concern ourselves with is the number of degrees of freedom, or as we call DOF. We want to determine the degrees of freedom of a mechanism. And what is DOF? DOF is the minimum number of scalar inputs needed to define the complete configuration of the mechanism. It is the minimum number of scalar inputs required. That is, if you have a mechanism, if you give so many inputs, and these inputs can be thought of as actuation. So, degrees of freedom also gives you the minimum number of actuations or inputs needed for deterministic motion. Deterministic word here is important because that is exactly what we want mechanisms to have. There is no random motion. If you give as many actuations as the number of degrees of freedom, then you know the position, velocity and acceleration of every member in the mechanism. This is what we learned for rigid body mechanisms or rigid body linkages. The formula that becomes useful to analyze mobility or to compute the degrees of freedom is the familiar one that all of you would have learned in your kinematics class, that is Kurzbach and Gruebler's formula. Kurzbach is usually given for 2 degrees of not 2 degrees of freedom for planar mechanisms, things that are alone in 2 dimensions xy plane, and Gruebler's is given normally for spatial or 3D, and those formulas are shown for the general case for the 3D as well as for 2D here. Here n is the number of rigid bodies and it is a misnomer that we always use the word links. Link normally means in plain language something that connects two things, but here we say it connects two joints. So, it is a kind of a misnomer, but people normally use links when we should actually mean rigid bodies. Okay? That is the n is that, and then Fi, which is here, is the number of joints that allow I relative motions between the two bodies they connect. So, every joint connects two bodies, two rigid bodies, and if I say Fi, then I indicates the number of relative freedoms that this joint allows between the two bodies it connects. So, if you have a revolute joint, that is a hinge allows one relative rotation, that is the relative motion that it allows. So, that will be called F1. Its number of such joints is what F1 will indicate. Similarly, Fi. And in 2D, we have the formula that 3 times n minus 1 minus 2F1 and then minus F2. In the case of 3D, we have 6 into n minus 1 minus 5F1 and 4F2, all these are subtracted. Here there is no F3, that is here F3 is absent, because if you say F3, it allows 3 degrees of relative motions. In 2D, every body has only 3 degrees of freedom in a planar mechanism. So, if you say F3, that means two bodies are not connected. Similarly, F6 is not present here, because again it does not make sense to talk about a joint that allows all 6 relative freedoms that exist between two bodies. So, it stops at F5 over here, stops at F2 in the case of planar mechanism. And these are some of the familiar examples for you. A 4 bar linkage where the n equal to 4, this is the one that is fixed, we call that 1, 2, 3, 4, and there are F1 joints, 1 degree from joints, 4 revolute joints, and there is F2, there are no 2 degree freedom joints, that is 0. So, now if we write degrees of freedom for this, it is 3 into 4 minus 1 minus 2 into 4 minus 0, that is 9 minus 8 equal to 1. It is a 1 degree of freedom mechanism. Similarly, we have a cam follower mechanism here, that also if we count n equal to 3 here, the fixed one, this is 1, this is fixed, and cam is 2, follower is 3, n equal to 3, F1 we have a pin joint there, a pin joint there, that is 2. We also have an F2 joint here, which is this one, that is a higher pair with a line contact, surface contact, that is 1. Now, if we do degrees of freedom for this, 3 into 3 minus 1 minus 2 into 2 minus F2, that is 1. This will be 6 here, minus 4 minus 1 1. In both cases we got 1 degree of freedom. These are things that are very familiar to you. Now, let us ask the question, if we have compliant mechanisms such as the ones shown here, this is a DACM. Since we are going to use it a lot, let me define that. It is displacement amplifying compliant mechanism, DACM. If we have such a thing, it may look complex, but we want to talk about degrees of freedom of such a mechanism, or what is known as Rollamite joint. This has flexible metal strip that goes around as shown here, or our nail clipper. How do you talk about degrees of freedom for mechanisms that have flexible or elastic segments in them? That is what we would like to address. Before we do that, let us just understand Gruebler's formula, rather we derive. So, if I talk about degrees of freedom, let us say we take 2-dimensional case. If there are n bodies, I will have 3n degrees of freedom, because every body in a plane will have 3 degrees of freedom, 2 translations and 1 rotation. Now, if there are F1 joints, that is joints that allow only one relative motion, that means that they are removing 2. So, I have to multiply by 2. 2 times F1, number of 1 degree freedom joints, then it will be minus 2 F1. Similarly, minus F2, because an F2 joint allows 2 degrees of freedom and hence it removes 1 degree of freedom. So, you have to subtract all of them, minus F2, that is how we get. Similarly, if I go to 3 dimensions or spatial mechanisms, we will have each of them will have 6 degrees of freedom, and we have to, of course, when there is a fixed one, we have to change that. We have to remove 3 here whenever there is a fixed one here, and that is how we get 3 into n minus 1 minus 2 F1 minus F2. And here in spatial case, this is the 3D or spatial, whereas this is planar. If there are n bodies, 1 we subtract because that is fixed, and 6 is what each body has, we have that, and then we have, I can just write it as I into Fi, where I goes from 1 to 5, not 6, because 6 degree of freedom joint does not make sense, no joint at all. So, whatever we have here, minus 2 F1 minus F2, depending on this should be 6 minus I. Okay. So, when I equal to 1, that is F1, it is going to remove 5 degrees of freedom. So, that is how we got the formula, 6 into n minus 1 minus 5 F1, 6 minus 1, 6 minus 2, if I have F2, that will become 4, and then 3 F3 minus 2 F4 minus F5. That is the interpretation of Gruebler's formula, right. Now, let us look at that extended to compliant mechanisms. So, we understand this part. Now, instead of calling F1, F2, F3, we are using NKJ, that is the number of kinematic pairs or kinematic joints that allow j relative degrees of freedom. Okay, this degrees of freedom DOF. Okay. But the difference is that here we do not just have n, but we have n subscript seg, meaning we have segments. We do not count bodies anymore, we count segments, and we say that these segments can be rigid, that is a traditional rigid link mechanism, or compliant or elastic segment. So, this will be elastic or compliant segments. You count all of them and that is your n seg. So, that part is familiar, but then we also have this one where we are subtracting not only the kinematic pairs, whatever degrees that they remove, but also we consider the elastic pairs, our NCJ. NCJ indicates the number of elastic pairs that allow j relative degrees of freedom. It is just like kinematic pairs, now we have elastic pairs. So, that part is also clear, but we have this new thing called n fix. What is that? N fix is the number of fixed connections. You may wonder why we need to include, but then there will be cases in compliant mechanisms where the elastic segment is attached like a cantilever connection to a rigid one, or two elastic segments can be connected to each other using this fixed connection. The fixed connection is one that does not allow any degrees of freedom between the two bodies, any relative degrees of freedom between the two bodies or two segments in this case, and each such thing will remove 6 degrees of freedom. We are again looking at a general 3D case, 6 degrees of freedom it will remove. So, if there are n fixed, that many fixed connections, we have to remove so many degrees of freedom. But the last one needs even more attention in this modification, which is addition. You see that this is not minus, addition. The addition comes because elastic segments have additional freedoms that they provide. Without that freedom, compliant mechanisms cannot even move or deform. Unless they elastically deform, we will not get any motion. So, we have to pay attention to this particular one, where it says NSCJ. NSCJ is called the segment compliance of J. Segment compliance can be 1, 2, 3, it is going up to 6 here in spatial case. In the planar case, it will be up to 3. Okay. And it is saying that if there are, let us say NSC1, that is one single segment compliance elastic segments are there, that will basically add j, meaning that 1, NSC1 we take j equal to 1. So, it will add 1 degree of freedom, that is why we have this plus sign. Okay. Let us look at the formula one more time. This part is the first one and second term, they are familiar. Okay. This is familiar, only thing is now we count the segments that include both rigid and elastic, and then this part is what was there in Gruebler's formula, and then this one we add because in a compliant mechanism there could be elastic pairs which act just like kinematic pairs, but have elastic degrees of freedom. N fix because occasionally we would need to have fixed connections among various segments in the mechanism, and this segment compliance is something that we will discuss a little bit more, so that we understand what the degrees of freedom means. Okay. One thing to note first is that the degrees of freedom given for a compliant mechanism in this manner actually gives the maximum degrees of freedom that are possible. Degrees of definition was minimum number of actuations needed, but now we are talking about degrees of freedom that is a maximum number of degrees that can give to provide deterministic motion. Okay. It can be anywhere from 1 to the number given by this DOF. So, 2D case also one can write. Let us write the 2D case. Note DOF is equal to 3 into n seg minus 1, and then minus, if I follow that notation of 2 n k 1 minus 1 NK2, those are the ones you can have, and then I can have 2 NC1 minus 1, let me erase this, minus NC2, these are elastic pairs, and then we have 3 N fix, and then we have plus the segment compliance, that is 3 N SC1 sorry SC3 plus 2 N writing here, one second. So, I am just writing the formula, plus if there is a segment that has segment compliance 2 and then segment compliance 1, that is how it is. Okay. If you look at the mechanism that is there, let me redraw it. So, here there is a rigid body, there is a rigid body here, there is a rigid body there. Okay. So, we have 1 and then let us call this 2, this is 3, this is 4, that is like a 4 bar linkage, and that is the rigid chain. Let us use a different color to show the compliant part. There is an elastic segment, there is an elastic segment, this is where the fixed connection comes. So, this elastic segment is kind of welded to this rigid one and similarly welded to the fixed frame 1. Okay. And then we also have a connecting thing here, which is this, and there is also a slider. Let me use a different color for it. Okay. There is a slider. So, if I call this 1, 2, 3, 4, 5, this is 6 and this is 7, this is 8. Okay. So, if we look at how many degrees of freedom this has, okay, how many segments are there? We counted 8. So, the DOF for it is 3 times 8 minus 1. We are counting both elastic segments, the blue ones 7 and 8 and the rigid ones 2, 3, 4, 6 and 5, and we have the fixed frame, that is 1. Okay. So, but we count everything 3 into 8 minus 1. How many 1 degree of freedom kinematic joints are there? 1, between 1 and 3, the 4 bar basically has 1, 2, 3, 4, and then we have prismatic joint here and there is also another joint there. So, we have basically, if I use in black, 1, 2, 3, 4 and there is 5 and there is 6 over there. So, I have 2 into 6, there are no NK2 joints, that is 0, NC1, NC2, NK2, they are not there in this one. So, they are all zeros. Okay. So, NK2, NC1 and then NC2 minus 3 times N fix. Fixed connections are there, there is 1 over here, there is 1 over here, there is 1 over there, 1 over there, meaning the 2 elastic segments are welded to, for example, elastic segment 7 is welded to 3 as well as 6, elastic segment 8 is welded to fixed frame 1 as well as 6. Okay. So, we have 4 fixed connections. I hope you see the important fixed connection compliant mechanisms. We could have put a joint there, that is also possible. Now, in this particular example we have fixed connection. Okay. There could have been a revolute joint between 7 and 3. Okay. And then we have this NC3, NC2, NC1, that is segment compliance. Choosing segment compliance, we need a little practice, but when you are in doubt you take the full one. Let us say we have 2 elastic segments here, let us take segment compliance of both of them to be full in planar case, that is 3. Segment compliance refers to in what ways the elastic segment moves between the 2 bodies that it connects to. Okay. Now, elastic segment is like a joint also, because it allows relative freedom between two things. A rigid body would not allow, only a joint would, elastic segment would. So, if I do that, if I take this, it will be 3 into 2, okay. That is I am taking this, then NSC2, NSC1 does not matter. So, in this particular case I get 3 into 7 minus 12 here, minus this is 12 and this is 6. So, what I have here, this is 21 minus 12 minus 12, that is 24, that is minus 3 overall and then plus 6. So, what I get is 3, and these 3 degrees of freedom can be interpreted. That is the first thing we need to learn. The 4 bar that we have here clearly has 1 degree of freedom, that we already know, that is 1 degree of freedom. And after that you look at this green one can rotate this way, that way, that is 1 degree of freedom, and the slider can translate. So, we are able to interpret the 3 degrees of freedom in this case in the form of rigid body modes that this has. As a consequence, elastic segments, their deformation completely gets fixed. Imagine that I position this red or brown 4 bar in one configuration, and then I rotate the green link, that is second degree of freedom, move this slider, then elastic segments, their complete deformation will be determined, and that is what we are saying. So, the formula here gives the degrees of freedom to be 3. On the other hand, if I apply less than 3, let us say 1, 2 for this mechanism, it will still be able to give you some motion. Just imagine that it is there and then I take this green one and rotate. Elastic segments will give you enough stiffness and they will move the 4 bar linkage as well. So, degrees of freedom for this linkage can be 1, 2 or 3, but not more than 3. That is interpretation. It gives you the maximum freedoms possible. It can be 1, 2 also. Okay. So, when you apply Gruebler's formula directly to this mechanism by treating 7 and 8 as rigid bodies, let us say whatever degrees of freedom you get, that will be the if it is less than 1, we say 1 degree of freedom is what is the minimum freedoms for a compliant one. If it is more than 1, whatever that has will be degrees of freedom. Okay. But this formula that we have for modification for compliant mechanisms will give you that many maximum number of degrees of freedom. Degrees of freedom definition still holds, that is minimum number of inputs required, but degrees of freedom itself, now we have a upper bound on it or maximum value. In whether you give 1 input to this mechanism or 2 inputs or 3 inputs, it will give you deterministic motion. That is what we want to have in terms of mobility analysis. Okay. So, 3D also the same thing, we have n fix and the segment compliance. Okay. So, 2D and 3D now we have understood. Let us look at a simple example. Okay. Here I have the fixed frame 1 and this moving body 2, and there is a elastic segment, in this case a spring 3. When I have that here, let us apply this 2D formula and then see what we get. So, degrees of freedom here 3 into 3 segments minus 1, and then there are no kinematic joints. So, this thing will not contribute, this one also not there, whereas this one is there. So, minus 0, fixed one. So, elastic segment is connected over here and over here, those are the fixed connections. So, what we get is 3 into 2, and then we have this segment compliant. Let us understand, if you take a spring, what is the possible deformation for it? It can extend and contract. We do not normally use springs to bend them. So, I can take this as j equal to 1. So, it will be 1 times how many such segments are there? NSCJ, that is 1. So, if I do this, this will be 3 minus 1 2, that is 6, this is 6 plus 1. So, I get 1 degree of freedom. I am happy because this has 1 degree of freedom, right. But if I want to take the segment compliance of this as more than 1, here I took 1 and that is why I have 1 degree of freedom. Instead, if I have, let us say, a bar with this one. I do not have a spring now, but I have a bar. If I have a bar, if I count, I will have again 3 segments. So, that does not change this number, and the fixed connection over there and over here, that does not change this number, it will be minus 3 times 2, whereas this number will change. Instead of 1, if I now say it has segment compliance 3, it will suddenly will have 3 degrees of freedom for this one. And we can interpret that. If I have a bar, it is like a cantilever beam where I can apply forces, I can apply force in that direction or in that direction. I can also apply a movement there. So, those are the 3 degrees of freedom. So, if I take a cantilever beam, here I am showing vertically going from spring to this to explain segment compliance. Instead, if I have a cantilever beam like this, we tend to say that a cantilever beam will have infinite degrees of freedom. That is not true. It will have, if I say the force is being applied only at the free tip, the force can be that way, this way or that way, and that is basically what we have just discussed. So, a cantilever beam has a segment compliance of 3, segment compliance of this equal to 3. When in doubt, you take the full. When you know, like in this case of a spring, you take it as 1 because the spring can only go up and down, right. So, to understand segment compliance, let us take a simple example. Here the number of segments is 4, they are indicated in the figure, the fixed frame 1 and the wheel 2 and the flat rope is 3 and the block is 4. Number of fixed connections, that is over here and over there, and NK2, there is a prismatic joint that is over here and there is a pin joint there, and then I have taken NSA 3 here as 1. The flexible rope has segment compliance of 3 because you should be able to extend here as well as go around the pulley. If you take that, you will get degrees of freedom 2. Again, these are the maximum freedoms possible for this mechanism. One freedom you have to interpret, one is the rotation of the pulley. After you do that, the block will be positioned somewhere, and then we can apply force here. We can contract it or extend it. Either way, we have 2 degrees of freedom for this, and that is it. If we give these freedoms, everything about this mechanism is fixed, including what happens to flexible rope. Instead of flexible rope, even if we have, let us say, a flexible strip which could buckle when apply force upwards, that still counts as 1 degree of freedom here, 1 degree of freedom for the wheel too.